The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
It's my honor and my pleasure to introduce you to the first speaker, who is Dr. James Aldred. A little bit about his bio, because it's pretty extensive and pretty impressive. Dr. James Aldred has over 30 years' experience in the construction industry in Australia, Asia, the Middle East, and the UK. He has different experiences and backgrounds all over the world in all different kinds of positions. I will not share the list, it's too impressive. But really noteworthy to say that he was an independent verifier for the construction of the Burj Khalifa in Dubai, the world's tallest tower. Currently, he is technical director with AECOM and is adjunct associate professor with the School of Civil and Environmental Engineering at the University of New South Wales in Australia. He obtained his PhD from Curtin University, and again, he's member and fellow of all different kinds of institutes all over the world, including ACI. He received an award for excellence from the Concrete Institute of Australia, an award for outstanding and sustainable contributions to concrete technology by ACI, and the prestigious George Stephenson Medal from the Institute of Civil Engineers. He describes himself as a pragmatic specialist who can work across disciplines, a practical researcher and a practitioner who can think outside the box to solve problems. And if you want to believe Dave Miller from the Concrete Institute from Australia, he's one of Australia's best. So allow me to welcome James Aldred.
Good afternoon, ladies and gentlemen, but Australia's also a long way away, so hopefully I can stay with you this afternoon. It's a funny time over there. Yes, I just wanted, well, as is often the case with an impressive structure that a lot of people know about, is it helps to get bums on seats, as they say, the Burj Khalifa. It is a very impressive building, and I think one of the unsung impressive components of Burj Khalifa is how much self-consolidating concrete was used in the project. Everyone knows how tall it is and how interesting it is, but I think SCC is an important component in the project. So the first question, which I think is quite an important question, because there's another even taller building coming up nearby, is why build super tall buildings anyway? And particularly in a place like Dubai, where there's not necessarily population pressures and so on. There is one component of super tall buildings that is actually really quite productive, and that is whenever we push the envelope of technology and we challenge those envelopes, we learn quite a lot. And so while there's a lot of sustainability people who would probably be horrified at Formula One racing, there's probably been nothing that has reduced petrol consumption more than Formula One racing, because of all of the technology that gets applied in reducing weight and improving the mechanics and the operation and the petrol efficiency of an F1 vehicle. And the same, to some extent, can be thought of when it comes to super tall buildings. And this is from the Council on Tall Buildings and Urban Habitat website, and you can see that there actually was quite an inflection between Taipei 101 and the Burj Khalifa. It really was ramped up, and the next tallest tower at 1 kilometre high in Saudi will also be another great leap forward. Very interesting part of that is that 30 or 40 years ago, if anyone had asked what would be the tallest building in the world, they would have said an office block, and it would have been steel, and it would have been in North America. And now, for the last 15 years or so, they've been wrong on all counts. We have had multi-use buildings, we've had concrete structures, and they've been in Asia and the Middle East. This is Burj Khalifa, and fortunately they were slow in putting up the cladding, so it proves that it actually is a concrete structure, sort of right up to that tippy top there. The piling, which was essentially 50-metre piles, 1.5 metre diameter, were with self-consolidating concrete, and these were in quite aggressive conditions of the order of 2 to 3 times seawater. The raft, which is essentially a 4-metre thick raft covering quite a large footprint, was self-consolidating concrete. That's impressive in itself because it's also holding some serious loads. The tower is of different grades of concrete. The original anticipated procedure was to use 80 MPa concrete just up effectively 2/3 of the concrete distance and height, then 60 MPa concrete beyond that. What ended up happening, however, was a sort of a rethink. As often happens in projects, people become a little bit more conservative at the pointy end, and they wanted to actually start to beef up the anchorages and for the steel structure which is on top, which itself is 200 metres high. So as one of the engineers described it, it was like building the Eiffel Tower on a tennis court. So it was sort of what was happening, but that's on the steel side of it. We're at concrete. We're in a concrete institute. So that's just an idea of the piled raft that existed here. Just looking at the raft mix design, one of the dominant factors in the design of the concrete for the raft was the requirement, SOM's requirement for 160 Fahrenheit or 71 degree peak temperature. And the original proposals had lower fly ash contents, and I proposed that it should be getting up to of the order of 40%, which it did, and it achieved all of its required properties. This is for the central portion, so this was about 5,000 cubic metres, or whatever that is, 6,500 cubic yards of concrete poured as a continuous pour, and this was primarily done through the night, but these were the slump flow values. Basically every single truck was slump flowed, and while some people might whinge about some of these numbers, I would say that when you're getting basically 700 plus minus 50, I think you're doing pretty well in your quality control. These were the temperature values that were being achieved, and you can see it's topping out at well below the limit. Another interesting part of this, which everyone should keep in mind when it comes to pouring these massive elements, is they hang on to their heat for a long time. And the other thing, this ramp up you can see here, is where someone decided, oh, we've hit our 20-degree temperature limit between the centre and the surface, and so this is when insulation is being put on this surface. In fact, to keep these temperatures, I'd actually water ponded the element for the early phase. But I think for people who've thought about this problem, some few days on after casting this concrete, that concrete is able to deal with that temperature differential without a problem. So I don't think that's a necessary requirement. But there were some concerns regarding the performance, the potential performance of an SCC under these kinds of sustained loads. And so people took some cores out of these things, and it's quite an operation taking these 10, 12-foot cores out of elements, but they are quite useful and quite encouraging. The fact that there are essentially, for what was a 50 MPa concrete, they're getting essentially 70 MPa through the entire section. Modulus was a little bit lower at the top surface, and this Coulomb value was a little bit higher, but then if you look at the x-axis, you can see that it's not all that high, actually. Just got better at the bottom, not better at the bottom, not worse at the top. And then looking at the more exciting part of the project, when it starts to get out of the ground, a number of different mixes were being considered for different parts, horizontal as well as vertical elements. The initial proposal for this project was to use a 10 mil aggregate, and they anticipated that there would be staged pumping up at about 400 or 500 metres on the building anyway. I actually looked at the grading curves for the different aggregates, and the 10 mil stone really didn't look more than, you know, a relatively coarse fine aggregate. And I said, well, I don't think anyone's going to be happy building the world's tallest building out of mortar. But the 14 mil stone was pretty good, because that was actually a sort of purpose-made aggregate. So very good grading curves and so on, which was very helpful. And as you can see, all of these mixes, particularly the 80 MPa mixes, are down at pretty low water cementitious ratios. More modest fly ash contents and decent silica fume contents for the cohesion. Not many job sites have this setting next door to them to be able to do a horizontal pumping trial for 600 metre long pipes, but this one did, because it was basically a demobilising of an army camp near town. If you can, pumping trials are fantastic, because you can really push the envelope. You can relatively non-destructively block the pump. And indeed, one of the things that happened here, which was very useful, was I'd told the premix company, don't use naphthalene-based admixtures for your horizontals and polycarboxylates for your verticals, because there'll be times when you'll be mixing these two concretes and you'll just turn it to jelly in the pump and you'll block everything up. Oh, don't worry about it. So this was a good way to prove that I was right, and they blocked up the pump and wasted everyone's time for about half an hour. But it's very, very problematic doing that, doing those kinds of blockages on site. But what I would recommend on a normal site, which doesn't have this kind of space, is that it's the good thing about pumping is that it's easy to start off with. And so you actually do have time to get things in better and to make modifications and so on. So if you put pressure transducers in at your pump and at the end of your horizontal or some way up your building, you can get your friction factor and calculate out what your performance is going to be over time. So this is the outcomes of those kinds of tests that were being done, looking essentially at the slump flow reductions. Obviously, Dubai is a relatively hot part of the world, so changes in slump flow were of interest. Unfortunately, at this particular stage, we weren't doing rheological measurements. The key parameter that was required is this friction factor, because essentially pumping super tall buildings, well, we've got sort of a heavy liquid, so that's just a hydraulic pressure, plus you've got to add in the friction factor for dealing with it. So the friction factor is a critical factor in here, as well as the cohesion of the system. And as you can see, dropping from a 20 mil stone to a 14 mil stone is dropping the friction factor to less than half. There's not that much of a change when you go to a 10 mil stone. proving that there is a criticality in the kinds of sizes of aggregates relative to the pipe. And these were some other effects, quite important, because, as we'll see a little bit later, one of the things you've got to keep in mind when you're pumping long distances is there actually is quite a lot of friction in the system. And for this particular job, virtually every cubic metre of concrete cast in a vertical element was cast at night. It would have contained reasonable amounts of ice to maintain these sorts of temperatures. Okay. And so the heating up was an interesting part of the equation. This is a pump station at the base of the project, and here's some rheological measurements going on the side. The good thing, even during production, for the tower, the slump flows were pretty consistent. Temperatures were also pretty consistent. Another very important point is the standard deviations of the underlying concrete were not bad. So ranging essentially between 3.5 to 4.5, something like that, for 100 MPa concrete is not bad quality control. And the reason that it's important is to keep in mind that the things that change strength are also going to be changing rheology and other things that are important. The advantage and the reason why people are changing over to pumping for super tall buildings is you can't pump steel. It can be windy. The crane has to be taking lots of stuff up. You can be pumping concrete to 3 different locations on the same site. Your crane can be moving what it needs to move. You can be pumping concrete even when there's windy conditions and so on. There are other considerations, though, because you've also got where you've got stiff stuff coming up and then going into what's essentially a relatively flexible climb form. That thrust as you're pumping can lead to anything up to an inch worth of movement or more, and wherever you go through these reducers and all the rest of it, you can quite easily end up with bits of your equipment shearing off because it hasn't been allowed to articulate. So some simple detailing is also very important to allow articulation at hard and soft points. And monitoring the pressures as you're going along is also important and very valuable, because it tells you, based on how big the pump capacity is, exactly how high you're about to be able to go. One of the interesting things that came out of the rheological measurements before and after pumping was that while there was a modest reduction in slump flow, there were these interesting effects of a reduction in plastic viscosity and an increase in dynamic yield stress. And the reduction in viscosity, because these were all happening in relatively short time frames, I think is primarily due to the heating up of the system before any other changes in hydration processes of being able to sort of kick in and start to make the system a little stiffer. And just some words of warning. This was the final pouring at 605 metres and so on. And what ended up blocking, because the contractor just kept on using the pump beyond what he was intending to do, because it was actually cheaper for him to continue, even though there was something like 13 cubic yards of concrete in the pipeline. What killed this concrete, and what kills most pumping operations, was a lousy slurry. You put wet slurry into a pump, particularly with a self-consolidating concrete or a high workability concrete behind it, you will destabilize the front portion of that, and you'll end up with segregation, and you'll start blocking up the pump, and that's what happened here. The other thing is, and this points out quite interestingly, that this thermal effect is that if you have delays, you can see that the outer section of the concrete, because of this friction factor, is actually tended to stiffen up compared to the interior of the pipeline. And this is going to be the next big thing that someone can talk about in a few years' time. I understand they're already on the 100th floor, or up 100 metres, so they're going for a kilometre high. So thank you very much for your time.
James, great job. Thank you very much. I've been on that job site a couple of times and got a chance to see the concrete as it's being cast, and it was on the verge of segregation after pumping because of a reduction of viscosity. Could you elaborate on when you went from one aggregate size to the other aggregate size, the viscosity or the friction factor dropped by half? Could you elaborate what are the reasons behind that? Is it...
Well, it's more interlocking activity. So in other words, at 20 millimetres, the actual pipeline is interacting and you're having boundary conditions, potential minor bridging problems and so on. So as soon as you drop down, those original trials were done in a 5-inch pipeline, even though the construction was done in a 6-inch pipeline. So that's the key. So in fact, I think you'd be quite well served under many circumstances to not go to a lower maximum aggregate size, because it's quite troublesome to do. A lot of people automatically with SCC just go straight into a very small maximum aggregate size, but I don't think that's necessary, and I think that's just lazy design.
So the shear walls that you were placing were not that highly congested?
Oh no, well, it wasn't. No, it was more to do with pumping,
yeah,
than it was to do with anything to do with the construction site, and that's the reason why making a compromise on aggregate size purely on the basis of pumpability. There are ways of dealing with it, because in fact, if you go for different pump diameter sizes, you're going to also go through reducers to get up to your placing boom, and there's going to be other points that you need to watch out for. And when you go to very big pipes, you know, these take many men to handle. These are difficult, but you know, the pressure's up at 200 bar. You've got to also, safety considerations are also very important.
Thank you very much.
And thank you very much for a nice lecture, James. What is the time of the concrete to pump it all 600 meters? And do you have no issue regarding workability loss with a various sheet?
Well, as you saw from those numbers, those numbers are actual pre and post pumping, and so that's taking a skip down and doing all the measurements on the ground. But in essence, the travel time, sort of a worst case scenario of pumping, would have been of the order of 40 minutes or so. These are not particularly long periods of time. I mean, the ambient temperatures can be quite high. I think the worst I ever had in Dubai was 40 degrees or 105 at midnight. So something of that order. So it can be a little bit punishing. But the biggest problem we had, and as Kamal just mentioned, most people are expecting, I'm pumping the concrete, therefore I need to have a slightly higher viscosity. But if you're putting ice in your concrete, the viscosity can go down as you're pumping the concrete. So be careful of that one.
Thank you.